Sir?
Yeah, I was muted. Sorry. Yeah. Okay. So where we? How many were? Anybody remember how many were we before? No. Okay.
Sir?
Someone asked you about the loss error.
Yeah. So the loss function, when we say a loss function or an error function, it's exactly the same thing. Yeah. So some people.
Sir, I have a question.
Yes, please go ahead.
Yes, I asked about the error function. I want to ask, why do we have the choice in training a model to choose what error function to use?
So every model, right, decides on an error function so that based on what makes sense. Yeah. So for instance, when we did linear regression, we had we used mean squared error. We could have used absolute differences between the values, right? But we used mean squared error because it was more friendly to differentiate, and it has a closed form solution. When it comes here to the logistic regression, again, I made some intuition, right? So I said I want to maximize the probability of the data being generated given the particular hypothesis or particular weight, and from this I drove the error function. Yeah. So every model has its own error function, and right, that's why they're different. And you don't.
Yes, but yeah. Sorry. Continue. Yeah. So, but why can we choose what error function can we make the model learn on to?
So we don't choose, right? It's the model is basically tied with the error function. So the error function, right, decides what becomes the model. It is the model. Yeah.
Yes, but I found an option, like when I was reading the documentation for linear SVM, I found an option to choose which error function, a hinge or a squared hinge.
Yeah, for instance, for linear regression or support vector machines or something like this, you could use L1. So that's what I was saying, right? You could use
yes,
absolute differences between the values or mean squared error. Yeah.
Yes, true.
And
so does it affect the training?
It affects the training. It might be one is better than the other, right? So if I used mean squared error, I can get a closed form solution. If I use the absolute error, I don't have a closed form solution because the absolute function is not differentiable. Yeah, at zero at least. So basically, you will have to do an iterative method, like the method we're going to use for logistic regression. So for some models, you have multiple error functions you could choose from. For some models, they're usually tied with one particular error function. Yeah.
Oh, okay. So I choose the best error function with testing, trial and error.
Validation, exactly. With validation.
Oh, with validation.
Yeah.
Okay.
Yeah.
Yes, and I have one more question.
Sure. Yes, Hamza.
Choose the best model if I different models. Is the cross validation accuracy the best determinant, or should I look at the F measure or something else?
So you can you can look at F measure, right? So I typically look at F measure in all my projects. I look at F measure.
So how would I know which one is better, like the F measure or the cross validation? Or
you can produce while you're doing cross validation, produce also the F measure. Yeah, so you can compute F measure. Or cross validation is just a method of splitting the data into train, validation, and validation, right? So you train on k folds or k-1 folds, and you validate on one fold. So while instead of computing error, you can compute accuracy, you can compute F measure. Every metric that you have can be computed. Yeah.
yes. So what? So usually F measure is the best metric to choose.
Yeah. So typically what you do is the following, right? During training, you do training based on the loss functions. You want to minimize the loss function. Okay, so you're really focusing on the loss function. Yeah, that's during training. And during validation, you could look at the other metrics like F measure, for instance, yeah, or something else. Yeah.
Okay. Okay. Thank you, sir.
You're welcome. So back to the cross entropy F. This is the formula we've achieved. Can you see all the slides?
Yes.
Okay, perfect. So this is the formula we've achieved. Let's look at it, investigate it a little bit. I have, right, an error function or a loss function that depends on the training examples, yeah, on n training examples. So summation from n equal 1 to n over the training examples. Similar to what we did in linear regression. It was summation from n equal 1 to n, the value of the prediction, so W transpose X, right, minus the actual label all squared. Yeah? The same thing happens here. So I have something that depends on the training data, right? Every point it contributes to the error. Let's see the error, right? The error is minus y e to the power of minus y n W transpose xn. So given some weights, yeah, you can compute this error. If W transpose xn is positive and yn is positive, right? So it's, then I get this value to be close to
0.
To 0, right? So I get this value to close to 0. So I get the len of 1 is 0, so I get almost no error. So if yn agrees with W transpose xn, either positive or negative, I get this value to be 0. Yeah, and so I make no mistakes. And if they don't agree, I get e to the power of, for instance, yn is positive and W transpose xn is very negative, right? I'll get e to the power of very large value, okay? And so I get, right, some error. So if they disagree, I get some error contribution. If they don't, if they don't agree, I get some error contribution. If they agree on the sign, right, I get some. Basically an error of 0, or almost 0. Yeah. So it's intuitive. It makes sense. But this is how we got it through the derivation. From likelihood, we drove this formula to get the cross entropy. So what I want you to understand, to be able to use the library later, is that, right, logistic regression uses this something, an error called cross entropy error, yeah, which depends on the training data. Okay. Now we'll see how do I minimize this cross entropy error. So given, right, n training points and the labels +1 or -1, how does, you know, the learning algorithm minimizes this cross entropy error? So that, right, the data is the weights, it gets you the best weights that generates the data, right? So the labels +1 and -1. Okay. So this is important. Yeah, you need to understand this. There's not a lot of mathematics here, but this is the most important part of the lecture. Yeah, because this is how you will be you will train the model. When you use it, you will train it, and also we're going to use the same algorithm for neural networks. So it's very important. Okay, so for linear regression, what did we do? We said the error was yn minus W transpose xn all square, average over all the data set, right? What did we do to get the weights W for linear regression? Anybody remembers?
Derivation.
We did derivation and set to 0, correct? And that led me to the pseudo inverse, so a closed form solution. So we did derivation with respect to W, we set to 0, we set it equal to 0, and we got, you know, isolated W in one side, and we got to the pseudo inverse, right, times Y. That's really the value of the weight. So we got a closed form solution. Okay. For logistic regression, we have, this is the loss function. I could try to do the same. I could try to differentiate with respect to W and then equate to 0. It will not lead me to anything. It will not get me a closed form solution. Why? Because I have len, I have e to the power of minus. So W is in the power, the negative. I have some len, I have summation. So it wouldn't lead to a closed form solution. You can differentiate. This is the function that you can differentiate with respect to W. But when you equate it to 0, you will never be able to get a closed form solution. Okay.
Should we distribute the len for both and then len of A plus like times Like ln of A plus B is ln of A times ln of B?
No,
Or
so
is it-
you do ln of 1 plus e to the power of my, you do 1 over x. So ln of x, the derivative of ln of x is 1 over x. Okay? Hang on a second, please. Yeah, I'll be back. I have to mute. And resume sharing screen. Okay, so somebody was asking me about the derivative of this with respect to w, right? So I have ln of x, assume this is x, so it's going to be 1 over x, and then you differentiate x with respect to w. You have 1 plus e to the power of minus y n w transpose xn. That's, you know, e to the power of x is the derivative of e to the power of x is e to the power of x, and then you drive the x, right, with respect to that. So it's like this chain rule, yeah. It doesn't matter. So we're not going to do this, or I mean, we're going to do it, but you don't have to worry about it. But the idea is the following, right? I cannot find a closed form solution if I do the derivative and equate to 0. So I'm going to do an iterative solution, iterative approach. Yes? Okay, questions? Somebody has something in the chat. Where is the chat?
No, Hamza was replying to me on something.
Okay. Right, good. Okay. So listen carefully, right? This is called gradient descent. That's the algorithm for logistic regression training and for neural networks, the same algorithm. Yeah, it's a very nice method. It's a general method for nonlinear optimization. So given a current value of W transpose of W, so it's similar to, we did this, something similar when we were doing perceptron learning algorithm. It was an iterative method. We did not have a closed form for the weights, so we initialized the weights and then kept updating the weights based on points. Yeah, we're gonna do the same thing here. We initialize the weights and then update them iteratively. We do some iterations over the weights. Yeah, each time we update the weights a bit until we reach a good end. Okay. So what is gradient descent? So given a current value of the weight W of t, so at this particular time point t, we take a step along the steepest slope. So here is the logistic function, the loss function of the logistic regression. Looks like this. It's a convex function. Yeah, with a local, with one minimum. Okay. I'll answer your questions yet in a second. Yeah. So now we start with some weights. Let's assume the weights was here. Can you see the slide?
Yes.
Okay.
Yes.
Assume that the weights are like the black circle. Yeah. So this is the initial weights that I have, random weights. Now I ideally wanna change the weights. Yeah. So assuming there's only a single weight, so it's a single weight. Yeah. So x-axis is a single weight. I want to update this weight. So I want to increase the value of the weight or decrease it. I want to increase it to reach the minimum, right? So ideally, right, if the weight was here or the initial weight was the black circle, so I need to increase the weight a little bit to get to the minimum, right? A little bit meaning, right, I don't know exactly how much. So I'm going to increase it a little bit, but I know that I should increase it. If the weight was here, initial weights were here, would I increase it or decrease it? If I increase it, I go this direction. If I decrease it, I go to this direction. I do what?
Decrease.
Decrease, exactly. So if I had the weights here, then I would go and decrease the weights a little bit to get closer to the minimum. Okay, so that's the method, how it works, right? So the direction I take is along the steepest slope. Yeah, so negative of the slope. I take the slope at my current weights of the loss function and take the direction of the opposite direction of the slope. Yeah, that gives me the right direction. That minimizes the function. Okay. So if the weights were here, I take the slope, right? Negative the slope, it will tell me go in this direction. So minimize, increase the weights a little bit. Okay. So let's put it in math. The new weights, so W of t plus 1 at iteration t plus 1 is going to be equal to the old weights, W of t, minus some step, right, times the direction that I should take, the negative of the slope, yeah, negative of the gradient. Yeah, the gradient, the slope is the gradient. Yeah, so what is the gradient? It's the differentiation of the loss function with respect to the weight. Yeah, and equate the differentiation or the derivative at the current values of the weight. So again, right, I have my current weight. All I have to do is decrease it or increase it a little bit, right? Increase or decrease depends on the gradient, so delta of in sample error or the loss function of the value of the weight, the current weight, and this is the step size, right? How much should I update it with, right? So it's a constant, yeah, a constant that tells me updated by this amount. Taking a small step, right, in the right direction. That's what I do. So eta is called the fixed learning rate. This is a very important parameter in logistic regression and neural networks.
Sir?
Yes.
How do we know that we are on the right track? If WT plus 1 was greater than WT, that means that we're not, right? We're not.
Yes. Yes. But if I take the derivative of the loss function, yeah, and do minus the derivative of the loss function at the current values of the weight, that would take me to the right direction. There's a proof for it, right? It uses right Taylor expansions and so on, but it's beyond the scope of the course. Yeah. So just believe me that if I take the derivative and do minus the derivative times some fixed right step, this will take me in the right direction to minimize the error. Okay. Now, Ziad's question, why is this better than PLA? It's not better. So again, right, it could be that PLA works on a certain data set better than this one, right? There's multiple models, yeah, out there. And your job is to try all of them and see which ones, or try at least few of them and see which one works best, right? PLA is not a strong model. Because it assumes the data is linearly separable, and if it's not linearly separable, you get into all these issues, doesn't converge, and so stop it after a certain number of iterations. Yeah. So nobody uses perceptual learning algorithm anymore, but it's a good introduction to machine learning. Really, I mean, logistic regression is a model that I suggest you always try. It's a strong model. Okay. Other questions? Good. So now back to the gradient descent. So again, the new weights would be the old weights minus eta, the learning rate, times the gradient at W of t, at the current values of the current weights. That's it. That's the algorithm. Let's first see how does the learning rate affect the performance or affect the algorithm, and then we'll write the algorithm. We'll see the pseudocode of the algorithm, and we're done. Okay. So when eta is too small, that's the step I'm taking, yeah, the learning rate. So when eta is too small, what happens? I'm taking very small steps, right, in the right direction, but very small steps. Okay, versus when eta is large on the right hand side. When eta is large, I'm taking very large steps, so I overshoot. Okay, what happens when eta is too small? What does this tell you?
Overfitting.
Not overfitting, it just tells
you take too much time to converge.
It really takes a lot of time to
Reaching.
converge. Yeah, exactly. Right? It will take me in the right direction. So the weights are being updated, they're getting better and better, but it's very slow. Yeah, so I'll run a lot of iterations until I reach my minimum or something close to the minimum. Yeah. When eta is too large, what happens? I might overshoot. I might miss the minimum. Right? So the weights are isolating, right? So they're changing significantly, And so I might end up, right, after a few iterations, I might end up really in a bad spot because I'm overshooting and I'm not reaching the minimum. Yeah. So overshooting, going from here to here to here to here randomly. And so eventually I might end up stop, because I stop after a certain number of iterations. Yeah. So I don't know if I reach the local minimum or not, right? But I stop after a certain number of iterations and I might end up in a very bad area. Yeah. That I overshoot, I miss basically the minimum. Yeah. So how do I set eta? It's a hyperparameter. How do I set it when I'm using logistic regression on a training set? Hyperparameter, how do I set it?
Try and error.
Yeah, what is try and error? Abbas, right? You said try and error? Who said try and error? Abbas?
Validation.
Use validation. Yeah, so we use validation. Yeah, so grid search, right? So yes, grid search to find the right value of eta. Yeah, so if you've done the assignment, then your assignment, you know what grid search is. It's a way of finding the setting the hyperparameters, and it uses validation basically. Yeah. So I try with different etas and see, right, what is my performance and on a validation set. Okay. Good. Here is the logistic regression algorithm. Let's read it together. This is, again, a very important algorithm. So what do I do? Similar to perception learning algorithm. I initialize the weights to some value. Let's say random or 0. We'll see why 0 is not recommended. So usually you put them as random values. Yeah. And then you iteratively do the following. Compute the gradient of the loss function, which is this formula. How did I get this formula from the loss function? The loss function looked like this. Yeah. If I do the derivative of this with respect to W, I get 1 over 1 plus this formula, and then I have E to the minus yn W transpose xn, and I have times minus yn xn. If I simplify it, I get yn xn, the minus goes outside here. I get yn xn over 1 plus e to the power of yn W transpose xn. Okay, so let's investigate this formula a little bit, right? Believe me that this is the derivative of the loss function, the cross entropy error with respect to W. So what do I have? I have a training set which has n points and the labels. Okay, so all I have to do is take this training set, right? Multiply the label by the feature vector, and then do 1 plus e to the power of yn, right? So the label times the current value of the weights times the feature vector, right? And that gives me, right, the gradient, a vector of gradients, yeah, for every dimension. I have d dimensions, I'll get the values in this gradient vector, okay? And so now to update the weight, I said the W of the new weight is equal to the old weight minus the learning rate, eta, times this gradient vector, right? This is d-dimensional vector. This is d-dimensional vector. I get a d-dimensional vector. That's the new weight, okay? What do I do now? I take stop, I repeat, so I compute the gradient. Now the only thing that changes here is the new weight, and see, right, what is my gradient? And then I update the weights. And then, you know, I get new weights, I update the weights, and then I stop after a certain number of iteration where the error doesn't improve. Yeah, so usually you stop after a certain number of iterations, 50 iterations or 100 or 200, depending on how much time you want to spend training. Yeah, so the more iterations you spend, yeah, the more time, of course, you'll have to wait for training. Yeah, and then finally you return the final weights back. Now in the library, you don't have to implement this. All you have to do is really say, okay, I want to set the learning rate to this value, right? You might set the initialization of the weights, right? You give it the training data, right? So you set up the algorithm so that it works with your training data. Yeah, so build the data set, right? Or give it the data set, and just let it train. So let it run for a few hours, right? And then after that, you stop it. So after a certain number of iterations, you stop it and you get the weights. Okay? Questions about the gradient descent algorithm or the logistic regression learning algorithm? Okay. Good. One final thing and we're done. So 2 more slides. How do I do predictions? So now I got the weights. How do I do the predictions?
Sir, after a knowledge race مش بالضرورة يطلع لنا the best error. So how is error?
So yeah,
the weight with the best error.
Yes, of course, right? Because I stop after a certain number of iterations, yeah? But ideally, I could build the learning curve and see that the error is decreasing, yeah? So the error would decrease. If I'm following the gradient descent, the error should decrease, yeah? Because of how I'm computing, I'm updating the weights. I'm updating the weights by taking the direction of the steepest slope. So the error should decrease. It will keep decreasing. Otherwise, you have a bug, yeah? So the error will keep decreasing unless, of course, your eta is, right, is too large. So if your eta is too large, as you say, we could overshoot. So we could have the error, right, decrease and then increase, right, because I'm overshooting, yeah?
What I meant here, no, how do you use number of items to get to the lowest possible error? We get the lowest error, then keep updating يصير يطلع الerror.
Yeah, so because it's an iterative approach, I cannot guarantee that it will get me the smallest error. Yeah. Who's talking, Ken?
Zia. Yeah, that's what I meant. So if you can't guarantee the best error, we do anything to choose the best error. غير إنه we just store it, أنا.
I'm not sure I'm following the question. So again, right? Typically I just stop after a fixed number of iterations. Yeah. So after a certain number of epochs, they go. Yeah, you stop.
Okay, but we don't guarantee the best error.
No, you don't guarantee the best error. Yeah.
Okay.
Okay. So basically,
okay,
you stop after the error is small enough for you. Okay.
Okay. Thank you.
You're welcome. Now, how do I predict? So now I got some weights. How do I predict? How do I use it to classify? Any thoughts?
We get h of x.
We get h of x. What is h of x? It's
the
theta
sigma
of W transpose X, right? So that will give me a probability. Theta of W transpose X will give me a probability between 0 and 1. So how do I say +1 or -1? Any thoughts? Let's say you give you a point X and you compute this probability and it's 0.9. Do you classify this point as +1 or -1?
+1.
+1. Yes, +1 because
the higher the probability and it's more towards the positive.
Exactly.
تكون صغيرة 0 which is negative.
Exactly, right? So if it's close to 0, then it's negative. If it's close to 1, it's positive, right? So you can, for instance, basically set your prediction y equal to +1 if this is greater than 0.5. So if this is greater than 0.5, you're in the positive side. If it's less than 0.5, you're in the negative side. Yeah, you can change the threshold, of course, right? If you want to be more strict, you make it larger here. If you want to be right, just typically it's set to 0.5. Yeah, theta of W transpose X is greater than 0.5. Here, I'm saying I have a right which has higher probability, the +1 or -1. Basically, that's what you decide the label based on. If the probability is higher than 0.5, then it's +1. If it's higher, if it's less than 0.5, then it means it's -1. Okay? And that's how it's used for classification. Good? Good. One last thing, and we're done. Regularization. Who remember regularization? It's important. Regularization is important. What is regularization?
We want some
prevent overfitting.
lambda.
Yes, to avoid overfitting, we said that we reduce the degrees of freedom. So we reduce the freedom of the weights. Yeah, we restrict the weights a little bit. Yeah. So how did we do this before? We said, right, instead of minimizing the sample error of W, I minimize the n-sample error and the weights, the summation of the weights. Norm of the weight square is basically the summation of the weight square. If you write this, fold this, it becomes sigma from d equals 0 to n, or I from I equals 0 to d, w squared. So I just wrote it in vector form. What is lambda? It's a regularization parameter. Yeah. Why I divide by n? Because it simplifies things, right? So it's standard to divide by n. Okay. So let's see. What is the error here? It's the cross entropy error for logistic regression. So let's see how this happens. We use a gradient descent as before, the same algorithm. So I go and update the weights, set the new weights equal to the old weights minus eta, the derivative of the thing I want to minimize now. It's the regularized, right, cross entropy error. It's not, before it was this, it was just this, minus eta delta of En W of t. Now it's minus eta, the derivative, or the gradient of En W transpose plus lambda n norm W transpose square. So norm W square, yeah, the current values of W square. Okay. So differentiation with respect to W. Again, this, we know what is its differentiation with respect to W. And we've seen it in the previous slide in the algorithm. Let's differentiate the new component with respect to W. What do I get? I have lambda over n W squared. What do I get?
2 lambda
over n
2
W.
lambda.
Yes, 2 lambda over n W. Yeah, so basically, okay. So then I get W of t plus 1 is equal to W of t, right? The current W, I mean, minus eta, the gradient of the loss function without regularization. So the logistic regression, this function, add the current value of W minus 2 eta lambda over n WT. Okay, what do? I take W of t common factor, and I get that the new W is equal to, it's exactly the same as the previous algorithm, but instead of just saying it's the old W minus eta, the gradient, it's now 1 minus 2 eta lambda over n, where lambda is the regularization parameter, times the old weight. Yeah, so you're regularizing the old weight a little bit, yeah, by multiplying it by this component. Yeah, that's the only difference. Okay, again, you don't have to worry about it in the library. You can just say, I want to use logistic regression and do some regularization using, for instance, weight decay, and you set you will have an additional hyperparameter, which is lambda, the regularization parameter. Yeah, so now we have 2 hyperparameters, the eta, the learning rate, and the lambda. Okay, right. Just one final thing. So when lambda is equal to 0, so basically no regularization, what do I get? If lambda is equal to 0, what do I get?
WT minus the rest.
Yes, so the old one, the non-regularized logistic regression. Yeah, lambda is equal to, I get the original exactly. Yeah, so W of t plus 1 is equal to W of t minus eta delta ensample, the gradient of the ensample error, or the cross entropy. Okay. All right. So now I hope you can implement this using sklearn. So I think we're gonna use TensorFlow maybe for the next assignment on Thursday. We're gonna learn. We're gonna use TensorFlow, which is the new library for deep learning. Yeah. So you get used to it as well. So you get familiar with it as well. Yeah. And all you have to do is you again set the learning rate, set up the data set. Set the learning rate. You say, I want to use the model that I'm trying to use, right? It's logistic regression, and just run it for a few epochs, a few iterations, and see and get the final weights. Yeah. Okay. Any questions? Okay. So I'm gonna share with you the recording as usual on YouTube, and we talk on Thursday. On Thursday we start neural networks.
Sir?
Yes, 1 second. So somebody has a question, right? So in regularization, we're trying to minimize the out of sample error, not necessarily the end sample error. Yes. So the goal of the regularization is to minimize the out-of-sample error. Correct. So I actually might increase the in-sample error, but in return, I minimize the out-of-sample error. Okay. So I try to avoid overfitting. Yes, who had the question?
Yes, me, sir.
Yes.
My question is, for the assignment, should we use grid search for all the parameters for every model?
Use what?
So, for example, for the polynomial kernel for the SVM, should we use all possible parameters, like the degree of the polynomial and the gamma?
Yeah, so you use some of them, right? Whatever makes sense. You don't have to try everything or set all of them using validation. So you can use some of them as default. But I want you to get accustomed to at least try setting some of them using validation. Yeah, using grid search.
Oh, okay. Yes, okay. Thank you.
You're welcome. Other questions? So Shadi has a session today will help you with a little bit with assignment 6, particularly grid search. Yeah, so we'll focus on grid search, I think. Okay, folks, we're running out of time. So I guess that will be it if you have no further questions.
Thank you.
All right.
Thank you, sir.
Yeah, take care.